This training video is intended to provide a general description of Electric Reliability Council of Texas, Incorporated's ERCOT's process for the Real-Time Co-Optimization Plus Batteries RTC+B program. This video is not a replacement for the ERCOT nodal protocols, operating guides, planning guides, or other binding documents. In the event of any conflict, the ERCOT nodal protocols, market guides, and/or other binding documents, OBDs, shall control.
Hello, my name is Ryan King, and I'm the Manager of Market Design at ERCOT. Today's training presentation will focus on how the ERCOT Real-Time Co-Optimization Plus Batteries, or RTC+B, will affect system dispatch in the future upon implementation of this new market. This recorded presentation is part of a larger set of recorded presentations on different topics to help support learning, development, and market readiness to market participants as we transition to the new RTC+B market design. This presentation and other recordings are available in the training videos section of the Real-Time Co-Optimization Plus Batteries Task Force webpage, available on the ERCOT website. This presentation illustrates how the outputs under real-time co-optimization, including market clearing prices, base points, and awards for ancillary services, will be determined under different scenarios. To illustrate this, we will use an internal RTC simulation tool that is also available for download on the RTC+B Task Force webpage. The tool uses a simplified electrical model comprised of 5 generators on a 6 transmission line system. Before we get into the examples, we want to illustrate what will change from today's market compared to how things will look under RTC. The current real-time market is designed to find the most effective set of resources for providing energy. Today's market is designed to reflect scarcity through a process that is outside of the SCED optimization, with ORDC and price adders. These price adders are combined with LMPs to form 15-minute settlement point prices. RTC is designed to find the most effective set of resources for providing energy and ancillary services. In contrast to today, scarcity will be reflected within the optimization, and scarcity pricing and the value of reserves is set by individual ancillary service demand curves, or ASDCs. Unlike today's market, the cost of ancillary services is factored directly into locational marginal prices. Ancillary services can be reallocated to access cheaper energy from alternative resources. The implications of this will be illustrated in the examples which we will go through shortly. This slide highlights the 3 scenarios that we will go through today. The first illustrates how RTC will derive the optimal allocation of ancillary services. The second illustrates how the ability to move ancillary service awards away from resources with helping shift factors can help resolve congestion and reduce congestion cost. And the third will illustrate how RTC prioritizes energy during scarcity and how the value of reserves and the cost of ancillary services is factored directly into LMPs under real-time co-optimization. This first scenario will illustrate how RTC will optimally allocate resource capacity to both ancillary services and energy in real time. To demonstrate this, we will increase the responsive reserve plan by increments of 10 megawatts and observe which resources receive awards. For this slide, you can note the initial system inputs, where some resources have higher energy offers and HSLs than others. For simplification, 4 of the resources have the same responsive reserve service offer and quantity. On this slide, we can see the initial system output with an ancillary service plan of 0. You can think of this system as an unconstrained or copperplate system, which focuses solely on the economic dispatch of offers to meet the 1100 megawatts of load. You can note here that the cheaper resources were dispatched to their HSL, and the LMP, which is the cost of the next megawatt of electricity, was set by G3 at a price of $30. Now, what happens if we start to increase the responsive reserve plan in increments of 10 megawatts? On this slide, we can see that the first 10 megawatts of RRS goes to G4. Now, it was the resource with the highest energy offer that was also offering to provide RRS. Under RTC, the optimization swaps 10 megawatts of G4's higher energy award for a cheaper RRS award. We will talk about market clearing prices for capacity for ancillary services in later slides. Now, let's increase the RRS requirement by a further 10 megawatts. Now, the first 20 megawatts of RRS goes to G4. Again, it was the resource with the highest energy offer that was offering to provide RRS. But now, the RRS capacity they offered is maxed out. So what happens if we increase the RRS plan by 10 megawatts again? If you look toward the bottom left side of your screen, the next 10 megawatts goes to G2. This is the resource with the second highest energy offer that was offering to provide RRS. We will now increase the RRS requirement by a further 10 megawatts. Again, you will see that the next 10 megawatts also is awarded to G2 and for the same reason as before. But now their quantity is maxed out. Let's increase the RRS plan by a further 10 megawatts. We see on this slide that the last 10 megawatts goes to G1, which is the resource with the next highest energy offer that was offering to provide RRS. So what is this showing? These scenarios show that when simultaneously co-optimizing or trading between energy and ancillary services, the optimization is prioritizing the need to serve load with cheaper energy and awarding ancillary services on units that are more expensive to dispatch. It is utilizing the gains from trade to determine the lowest cost solution to meet both energy and ancillary services. Now let's look at the calculation of ancillary services or the market clearing prices for capacity. What happens to system cost if the AS plan is increased by 1 megawatt? We can see on this slide that G1's RRS award increased by 1 megawatt, G1's energy award decreased by 1 megawatt, and G3's energy award increased by 1 megawatt. How do we determine the market clearing price for capacity from this information? This slide will calculate the market clearing price for capacity, or MCPC, which reflects how much it cost in the objective function to award an additional megawatt to satisfy the ancillary service demand curve. To do this, we need to look at resource award changes. G1's RRS award increased by 1 megawatt, an increase of $5. G1's energy award decreases by 1 megawatt, a decrease of $14, and G3's energy award increased by 1 megawatt, an increase of $30. Now, if we sum these numbers together, we get an MCPC of $21. This MCPC can be thought of as the shadow price of the ancillary service constraint, which is the cost in the objective function to award an additional megawatt to satisfy the ancillary service demand curve. Now let's focus a bit more on G1. So what does it mean to make G1 indifferent? We know that G1 via their offer was willing to provide energy at $14 and the locational marginal price was $30. When G1 was awarded an additional megawatt of RRS, the opportunity cost needs to be factored into the market clearing price for capacity for responsive reserve service. In this case, the opportunity cost of G1 providing RRS is the lost revenue they would have received from selling energy. This cost is factored into the market clearing price for capacity so that G1 receives the same operating profit it would have received from the energy market. In other words, by factoring the opportunity cost of selling energy into the MCPC for RRS, G1 will now receive the same operating profit effectively, making it indifferent to the scheduling of its capacity for energy or ancillary services. The chart at the bottom illustrates that it will receive the same operating profit under each circumstance. So by factoring opportunity cost into prices, the optimization process also ensures that resources are not incentivized by prices to deviate from their reward. Now we will look at a second scenario. This scenario will illustrate how RTC will adjust ancillary service awards to alleviate congestion. To do this, we will decrease the transmission limits of lines and observe the rearrangement of awards to manage congestion. Note that we will start off with all lines having the same limit and the same maximum shadow price. Note the initial system output with a 67 megawatt responsive reserve service AS plan. Note that none of the lines are approaching their 1000 megawatt limit. What happens if we reduce the transmission limit of L6 to 75 megawatts? So what we observe on this slide is that the RRS award on G1 decreased and the base point increased, which allows more energy dispatch to help alleviate congestion and cost on the constraint. The RRS capacity was temporarily awarded on G5. Now, a couple of things to note as well is that this is a very small system, so it would not always be the case that the AS is awarded to a resource on the hurting side of a constraint, and also that operators have manual overrides if they have concerns about the deliverability of awarded ancillary service capacity. For the purpose of this illustration, the key takeaway here is that by moving ancillary services off of the resource on the helping side of a constraint, RTC can help reduce congestion and cost. Now let's look at the locational marginal price in Austin at bus B. Due to its congestion, line 6 has a shadow price of $36.63. System lambda is $32.72, and bus B has a shift factor on line 6 of negative 0.11. In order to calculate the LMP at electrical bus B, we need to take system lambda, or the shadow price of the power balance constraint, minus the sum of the shift factor impact of bus B on constraint C multiplied by the shadow price on constraint C. Line 6 is the only constraint with a shadow price, so there will be only one term in the sum of shift factor times shadow price. And if we plug those numbers from the previous slide into this equation, we can calculate the LMP at this bus at a value of $36.88. We'll now look at a third scenario. This scenario will illustrate how RTC prioritizes energy over ancillary services during scarcity and how these penalty costs of going short on ancillary services is reflected in scarcity prices. To do this, we will increase load and observe the relationship between supply and demand as well as price changes. This slide shows the initial system configuration. Note here how close each generator is to its maximum capacity to serve load and meet the ancillary service plan. So what happens when we increase the load in Austin from 419 megawatts to 420 megawatts? On this slide, you can see that locational marginal prices have spiked. At this point, all generators are at their maximum capacity, so total HSL is equal to total load and ancillary service plan. It is not physically possible for generators to serve an additional megawatt of load, so the price of the next megawatt will require going short on ancillary services, which will incur a high penalty cost in the objective function, and this is reflected in the high LMPs we observe here. This slide also illustrates again the idea of opportunity cost. The $24 we see included in the LMP is the $3,000 ASDC penalty price plus the delta between the G4 energy offer of 29 and the RRS offer of 5. This is another example to show how G4 will be indifferent to its capacity being used for energy or ancillary services. Now what happens when we increase the load by a further 5 megawatts? On G4, 5 megawatts of RRS were sacrificed for energy, but this was not awarded elsewhere in the system. Since the penalty price for going short on energy, the undergeneration penalty price is $7,000.01, is greater than the penalty for being short on responsive reserve service, energy was prioritized. The penalty for being short on RRS is determined by the ancillary service demand curve. We are short 5 megawatts of RRS, so you can see in the top middle graph that we have moved from a $3,000 penalty price to a $5,000 penalty price on our example ASDC curve. What happens if we increase the load at Austin another 5 megawatts? So the total load without the AS plan is equal to the total system generation capacity. Now all ancillary service awards were converted to energy due to its prioritization. System lambda and all bus locational marginal prices are equal to the undergeneration penalty of $7,000.01 per megawatt hour. The system cannot serve an additional megawatt of load. An important thing to note here is that this scenario is illustrative only. In reality, ERCOT operators would undertake other control actions, including up to firm load shed, to maintain a minimum reserve quantity. So to sum up the discussion today, the previous examples highlight how RTC will impact prices, awards, and dispatch under different scenarios. What we tried to illustrate today is that when it comes to scheduling, real-time co-optimization can maximize the gains from trade between energy and ancillary services every 5 minutes to more efficiently and reliably serve load. RTC also provides for the ability to better manage congestion and cost by moving ancillary service awards away from resources with helping shift factors so that they can be dispatched to solve congestions. In terms of pricing, scarcity pricing and the value of reserves are set by individual ancillary service demand curves, where the cost of the ancillary service is factored directly into LMPs under real-time co-optimization. Finally, market clearing prices for capacity reflect the opportunity cost of providing ancillary services. That is, that they account for the operating profit as a function of offers that a resource would have received from providing energy, thus making the resource owner indifferent to its capacity being utilized for energy or ancillary services. This concludes today's training presentation. Please be sure to check out other RTC market readiness training offerings available in the training videos section of the RTC+B Task Force webpage. Thank you very much for your time.